share. You can see my desktop. Okay, all right. So in today's class, we will basically talk about this transmission lines. So you have read about transmission lines, right? Yes, yes. So as they transmit energy, there is some loss associated with transmission lines. So you know about those losses as well? Reflection, and there can also be like resistance related losses. Hello? Hello? Audible? Okay, okay, fine, fine. Okay, okay, okay. So the thing is that, I mean, yes, so losses can occur because of resistance, and like you said, there is reflection of signals which occur. So when there is the load is not matching with the impedance of the input impedance and the load impedance don't match, then there is reflection of signals, and that reflection can lead to standing waves between the reflected wave and the incident wave, right? So in that way, there can be standing waves as well. So that can lead to losses. So this is what this assignment basically talks about, like what kind of losses can occur in general in case of transmission lines. So in the first question, it says that there is a lossless transmission line whose length is 60 centimeters and it operates at a frequency of 400 megahertz. And the line parameters, the inductance per unit length is 0.36 microhenry per meter and capacitance is 100 picofarad per meter. So using this information, we have to find the characteristic impedance, the phase constant, and the input impedance when the load impedance is equal to this. Okay, so how do we proceed with this problem? We know that the characteristic impedance is given by root over z by y, where z is r, this is known, no, r plus j omega l, and y is g plus j omega c. So r is this resistance, g is admittance, and l is the inductance, c is the capacitance, right? So since this is a lossless circuit, that's why r equal to g equal to 0. So there is no resistance of any sort. That is why the characteristic impedance is root over L by C, right? Okay, so that's why it is 60 ohm. So this is how one can obtain the characteristic impedance. Similarly, next one is the phase constant. So phase constant can be written in terms of this propagation constant, which is root over z into y. That is root over r plus j omega l into g plus j omega c. Now since r and g are equal to 0, so this turns out to be j omega root over lc. So always for this lossless transmission line, since r and g are 0, so propagation constant will always be j omega root over lc for lossless case. So this propagation constant can be written as alpha plus I beta, right? From that we can obtain the phase constant, which is beta. Right? Okay, okay. And similarly, you're given the load impedance of ZL equal to 150 ohm. So then input impedance can be written in terms of the characteristic impedance and the load impedance with this formula. So if you calculate that, then you can obtain your answer. Right? Okay. Huh? Okay, okay, got it, no? All right. So the next question was the one which you said that about reflections. So standing waves, they are formed on the transmission line when which of these cases? So you said that standing waves are formed because of, yes, right, right. Huh? Hmm. Hmm. Yes. Yes. S- So correct, correct. Yeah. So the correct option is the first one. Because only when they match, then the reflection coefficient is zero and there is no reflection of any wave. Otherwise, there will be reflection of the incident wave and that can lead to formation of standing waves. Right? Okay. So then the next question, that is question 5, it says that we have a distortionless line whose characteristic impedance is 50 ohm and the attenuation is 20 mmp per meter. Okay. So the phase velocity is zero point 0.6 times the velocity of light in vacuum. Then what are the line parameters R and L? So over here you need to look at the formula for distortionless lines. Like earlier we had a lossless line, this time we have a distortionless line. So you know about this condition for a distortionless transmission line, right? That R by L is equal to G by C. Okay. So using this condition we can obtain G equal to RC by L. Now we have to obtain basically R and what is that? L inductance in terms of the characteristic impedance and whatever that has been given to us. So characteristic impedance can be written as, like we saw earlier, R plus j omega L by G plus j omega C. Now you take R and G common from here. Sorry, you take L common in the numerator and C common in the denominator. Then you get root over L by C into this thing. Now since R and G are equal, so this part and this part are equal and they cancel out and then you have root over L by C. Okay, so this is the characteristic impedance for a distortionless transmission line. Now the attenuation constant is given by root over R by R into G and G we saw is equal to RC by L. Now root over of this thing is basically R into root over C by L. Now root over C by L is 1 by Z0. That is how you have this factor of 1 by Z0 here. So alpha is nothing but R by Z0. So that is why R is equal to alpha into Z0. So you can see in terms of alpha and Z0 we found out the resistance of the line. So similarly, in order to find out the inductance, we use this formula for this propagation constant. So for this distortionless transmission line, you will find that the propagation constant is equal to this. That is R by Z0 plus j omega root over LC. So here also the phase constant is again omega into root over LC. Right? Huh? Uh-huh. Oh, okay, okay. So if you open this bracket, okay. So if I take L common from this part and C common from this bracket, then I have within root LC into R by L plus J omega into G by C plus J omega. Now R by L and G by C are the same quantity, right? So that is why this is actually a square of R by L plus J omega, and since you have a root, the square gets cancelled out and you only get this thing. And you have a root LC factor here. Okay. So that is how you get this thing. So R by Z0 plus J into omega by omega into root over LC. So here also phase constant is omega into root over LC, and phase velocity can be defined as omega by the phase constant. So then phase velocity can be written as 1 by root over LC. Now if you multiply the numerator and denominator by root over L, then you get 1 by L into root over LC, which is equal to Z0. So this is basically z0 by L. This is equal to phase velocity, and from this you can find that L is equal to z0 by U. Okay. So in this way I have what is given to me, alpha is given to me, z0 is given to me, and U is given to me. So using these three quantities I can obtain L using this equation and R using this equation. So if I put these values I get L and R like this. Okay. Okay. So what is the next question? Which one is not correct regarding lumped circuit regime? So which of these four statements are incorrect? Which of these three statements, in fact? Lumped circuit is basically that circuit diagram which you draw, remember, when you calculate the resistance. So you have a resistance connected to an inductor, and that is connected to a capacitance and a shunt resistance in parallel, right? So you're representing your transmission. Yeah, exactly. RL and GC. So that RLGC circuit, yeah, RL connected to G and C. Yeah, right, right. So that diagram which you have, that diagram actually represents the resistance of the entire transmission line. So you're representing the resistance and the properties of the transmission line in that small circuit diagram, right? So that small circuit diagram is known as a lump circuit diagram. So in case of a lump circuit diagram, what happens here? Let me see. So a transmission line is a very long length segment, right? It spreads over hundreds of meters, and you're representing that on a small diagram. So in the lump circuit diagram, the physical dimension is much less than the wavelength of the signal. So this is one thing we have to consider, that over the dimension of the lump circuit which we are analyzing, the wavelength of the signal does not change appreciably. Okay. Hello. So that is why the first statement is correct, that in lump circuit the physical dimension we consider is less than the wavelength of the signal. Okay, okay. Second one is also correct. Maxwell's equation can be written in terms of simplified quantities when the physical dimension is much less than the wavelength of the signal. So Maxwell's equation can be simplified. So this follows from this. And lastly, what is said over here is that the RLC parameters are individually concentrated at discrete points in the circuit. So this is also true, right? You have resistance at one point, L at one point, C at another point. So they are individually concentrated at discrete points in the circuit, right? Okay, understood this thing, no? Okay, okay. So all these three properties are properties of a lump circuit diagram. Okay. So in reality, all these three statements are correct. In the next question, for a high frequency transmission line, which of these statements are correct? If you have a high frequency transmission line. Huh? Yeah, resistance will be small. And what else? Right, right. Antenna size is small. Resistance is also small because you have. Yes. So one of the factors will be omega L much. Resistance is more, you're saying. Why? A small size will have a lesser resistance, no? Haha, so that. Right. Right, right. So that is why omega L will be much greater than. Yes, yes. Right, right. Right, right. So that is why you need a smaller antenna for that. Right, right. So one of the factors is omega L much much greater than R. That is one condition, right? Because omega is your frequency and R is resistance, so omega L much much greater than R is one condition. And the other condition is, what is the omega C condition here then? Hmm. Capacitance is less, but omega is more. So you know that capacitive resistance, that is actually 1 by omega C, right? So the opposite of that is conductance. That is omega C, capacitive conductance, what is called. Right. So if omega is very large, then omega C much much greater than G, right? So the condition for high frequency transmission line is this one, where omega L is much much greater than R and omega C is much much greater than G, right? You got it? Okay. So question number 8. Okay, if characteristic impedance is the same as load is impedance of a transmission line, then what is it called? It is matched, right? Matched. Yes, it is matched. So like you said earlier, there won't be any reflection if you have matching over here. Hmm. So question number 9 says that the primary parameter which is associated with electric charges is what? Out of these three, which one is the one associated with electric charges? Hello? The connection suddenly went off, I think. Hello? Hello? Yeah, the connection went off suddenly. Wait, I'm sharing my screen again. Yeah, yeah, wait, wait, wait. Uh, Breaking, no? Yeah, I think the it's a connection problem. Okay, okay. So question number 9 here. Yeah, so this is capacitance, right? Hello? Hello? Yes, audible now. Yeah, can you hear me? Yeah, yeah, capacitance, this one. Hello? 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 Audible, no? Yeah, yeah. Okay, okay, all right. Wait a minute. You can see my screen, no? Uh, Hello? Is my. Okay, okay, all right. Okay, 10th question is that there is a 30-meter long transmission line lossless with a Z0 equal to 50 ohm operating at 4 megahertz, and it is terminated with a load resistance given by ZL equal to 70 plus 40 J into 40 ohm. Okay, so what is the standing wave ratio in this line? That is the question. So you know about reflection coefficient? Is it what? Yeah, yeah. Exactly, yeah. Yes, right, right. Uh-huh. So once I get reflection coefficient, I calculate the magnitude, and then the standing wave ratio is basically 1 plus mod gamma by 1 minus mod gamma. Right. So its standing wave ratio is basically the maximum to minimum of the voltage that can go. Right? Okay, so this is how you calculate standing wave ratio. So those are all the questions I had to discuss. Is there anything else you want to ask? Or any clarifications which you have? Huh? While solving problems that you're. Oh, you're facing difficulty while solving problems. That's what you're saying. Okay. Okay. Huh? Okay, okay. So what I do is that when I'm given a problem, so I look at what is given to me, the information that is given to me in the problem. Okay. So for example, in this thing, the information which is given to me is this input impedance and the load impedance, and I am told to find the standing wave ratio. So since I have to find the standing wave ratio, first I have to calculate what is the formula to calculate standing wave ratio. So that was, for example, 1 plus mod gamma by 1 minus mod gamma. And then where does gamma come from? That is the next question. So I know that gamma can be written in terms of Z0 and ZL. So like that, I go step by step as to, okay, I have this thing, now I have to calculate this thing. Now to calculate that thing, something else is required. What is that something else? So if you go step by step, you will find that you will reach a point where you can calculate your final quantity with all that is given to you in the question. So that is like how I proceed while solving problems. Okay. So yeah, you just have to go step by step. Like you have to like go step by step and make sure that, and you have to recheck your steps, like when you're going from one to the other. Like if you make a mistake in one step, then probably you'll find that at the end your answer is not matching, or you're not able to get the correct answer at all. So then you need to recheck where you've gone wrong. So yeah, those things are all there. But if you go step by step, it is possible to solve these things. Okay. Okay, okay. All right. So next day, I think we'll meet on Friday only. Yeah. So today's class I had to shift because I was traveling on Friday. That's why. So next day we'll meet on Friday only. No problem, no? Okay, okay. ठीक है. All right. Bye then. Yeah. Tell me. No, no, no. Yeah, I'm studying doctorate only. Yeah. PhD. Uh-huh. All right. Yeah. Okay. Bye. Hmm.